Thanks for coming, everyone. My name's Mark. I work at Thinkst. This year at Black Hat we had this talk called Fighting the Previous War. The Aws guys asked if we'd do it back here, and I said, sure, why not? So, kind of quickly, we're a company called Thinkst. Mostly what we do these days is a product called Canary. You'll see we throw that brand everywhere. I've got spinners and stickers, but we'll do that afterwards. Mostly this talk is a collaboration. So Harun and I delivered the talk, but actually lots of the work was done by the rest of the guys. So there's Aws, who's sitting over there in the back, Jason, Nick, and Max. And so these guys helped us with various parts of the talk. So if we dive into this talk, and it is fairly long, we should, in Vegas we managed to do it in our 50 minutes, but we had the pacing down. So as Christo said, we'll do questions hopefully at the end rather than have a discussion halfway through or midway through. So if we come back to why are we here, a while back, and specifically in 2009, we did a talk, so Harun, myself, and a colleague of ours at that point, did a talk called Clobbering the Cloud, which that one was actually at Black Hat and Recon. And the world was a different place. The cloud was just coming into it was just sort of starting to become a thing. The US was in a very different place, president-wide. And as the cloud was becoming a thing, there was, and again, you have to sort of throw yourself back in time now, but you may remember if you were around doing stuff at that point, there was a lot of pushback about the idea of the cloud, what it was, and there were lots of voices at that time who were saying, the cloud is nothing different from just hosted stuff. It's just a hosted application somewhere else. It's not different, the attacks are the same, there's nothing new here. And what we were saying, the point of the last talk was to say, hold on, it is different. There are different attacks, the environment is not the same. And so in that talk 8 years ago, we showed a bunch of what at the time were, we thought, interesting attacks, and the talk got some attention at that time. And so I'll give you some idea of what those sorts of attacks look like and why they were different from other attacks that were present at the time. So 8 years ago, memory corruption was a huge thing. Web application stuff was all over the place. On AWS at the time, and it's similar now, you could go and launch your virtual machine. You would pick a virtual machine from a list of possible virtual machines you could launch. And those virtual machines at the time were ordered by their identifier, their AMI ID. That identifier was randomly generated, and so the simple attack in that case is, let's keep regenerating AMIs until we get an AMI ID that's low enough, which pushes our machine to the top of the list. So Amazon ships with, or at the time they had a few hundred, I think it was a few hundred AMIs that were accessible. We managed to push our AMI to the top of that list. So it means anyone who's looking for an AMI will run the one at the top of the list because it's just there. It's ordered by the AMI ID, and our stuff gets run. And so that's what this series of screenshots about this is the previous work shows. This is us brute forcing those IDs, and then in the end we get AMIs at the top of the list. And that style of attack wasn't something you had to worry about, except now when you're in a cloud environment, this is shared resources, shared infrastructure, and you have, as a user, the ability to affect it. So this was an example of a new style of attack. We had a look at the resource limitations that at the time Amazon put on you. And just like in present day at AWS, you have resource limitations. At the time, you also couldn't launch thousands of virtual machines. But at the time, there was open sign-up, and there was like a free tier where you didn't need credit card information. So that style of attack was fairly simple. We have a user who registers a virtual machine, takes him and launches it, takes about 3 minutes. Inside of that virtual machine, we run scripts which register a whole bunch of new users. Each of those users launch their own virtual machines inside each of those virtual machines. So virtual machine registers users, each of those users launches their own virtual machines, and very quickly this scales far past what you're supposed to be able to do, right? And that style of attack, again, is not a memory corruption issue. It's not a straight web application vulnerability. It was a different type of attack. And so very quickly you get into ungodly numbers, and theoretically Amazon falls over. But of course, we didn't go that far. So at the time, what we were saying, and again, this is 8 years ago, what we were saying is, this is different, and it'll need different thinking. Okay, us 8 years ago. We're now 10 years later, and sorry, not 10 years later. We're now 8 years later. We use AWS significantly in Canary. So with Canary, we run hundreds of instances, and we use lots of the AWS services to help us deliver our product. So we're quite intimate with what we do and how people can use AWS. And with the benefit now of 8 years, what we now say about the cloud is, this is different, and it'll need different thinking, right? And part of this is because our own view of what the cloud is has also changed, and we'll touch on that shortly. So it used to be the case that we just looked at the cloud as a way to launch virtual machines somewhere else. That's changed now for our view, and the people who designed AWS and were building it 8 years ago I assume had the vision where at the time they didn't just see it as a bunch of virtual machines. But certainly that was our naive view of the cloud 8 years ago. We can launch virtual machines. Now it's much more different, and we're going to touch on this in a little bit. So, and what I should give you an aside here, you'll see in the talk that it seems like we sort of repeat some stuff. Effectively, we had a division between Harun and myself with two different halves of the talk. I'm giving both of them, so if it feels a little bit disjointed, just imagine I'm now two separate people. I'll give you the signal when I change personality. Okay. So we're going to talk about differences in footprinting, exploitation, post-exploitation, and persistence on a cloud level. We're going to come back to the same sequence of steps, but specifically tied to AWS. But for now, let's deal with this more broadly. And if we look at footprinting, it's our view that this has always been undervalued. So when Harun and I used to do penetration testing, this is a little while ago now, footprinting was always a very strong part of an external assessment, and we'd spend up to 25% of the time just on doing footprinting, because you're looking for the one machine that has not been has been left out from patch cycles, or the one machine that's sitting there with out-of-date software, default whatevers. That's how you're going to break in. But that only works if you have a strong understanding of the footprint. And so footprinting is this thing that, for the most part, was not treated with the same amount of effort, but usually gave you lots and lots of value. These days, in the cloud, whatever that means, the idea of footprinting becomes much harder, because it's not only about the services that they run, but it's also about the services they use. And in a world of microservices, this becomes much, much harder. So who here is a sysadmin? Just like anyone? Okay, a few people. Who has set up SendMail, QMail, Postfix recently? Recently, like, okay, so like one person has set those up. If you're building a system that needs to send transactional email, by and large, you're going to use Mailgun, SendGrid, one of those. You're not setting up your own mail server, right? Why? Like, you have to worry about, is your SPF right? You have to worry about DMARC and all of that stuff. Or you can just give it to Mailgun and they send it for you, and the stuff winds up in someone's Gmail inbox a lot more regularly than if you try and do that yourself. So you're not going to do it yourself. You go to a microservice. The same for sending SMSs. Like, if you're going to send SMSs, you're going to use Twilio, one of the other ones. So, I mean, it sounds fairly obvious, but when you use these, it extends your attack surface. And this has sort of subtle implications. And there's a really nice example of this. So last year, or no, earlier this year, I think, there was like a crowd who posted their success with getting a bug bounty from Uber. And like, I won't go into the full details, but the short of it was that Uber used to use, or uses SendGrid to send outgoing email. So Uber uses SendGrid to send email. Inside of SendGrid, there's a way that you can claim ownership of domains. And it turned out that someone who was not related to Uber at all was able to claim an Uber domain in the SendGrid interface. It wasn't a bug specifically in SendGrid. Like, it was effectively, it was a flow that you followed within SendGrid, which Uber had not followed. And it left it open. And someone was able to send an email through, or send an Uber email, but to themselves, and they were able to claim this domain. That person then set up a webhook and then got every outgoing email that Uber sent, right? So every time Uber sends an email by SendGrid, they call a webhook, and these white hat Nepal guys, white hats in Nepal, also got a copy of Uber's emails. And they got themselves $10,000. But there's a few things that are noteworthy for this. Like the one that's super interesting is they put out a video on this attack where half the video is them struggling to set up a webhook endpoint so that they could capture the incoming mail. So that sort of gives you an idea of where the attackers were in terms of skill. Like half the video is them trying to set up a webhook endpoint when you could point it at request bin or one of those other ones. So that, they thought that that was the hard part of the attack. So not technical attackers, they're reading Uber's email because Uber relies on these microservices. And for the security team at Uber, trying to understand what your exposure looks like when your developers are using microservices is really tricky. And if you're a tester, this becomes even harder. Is SendGrid in scope for an external company doing a pen test on Uber? That stuff's not clear. And how would you even know that they are using these microservices, right? So would you know if it was being attacked, and would you know if SendGrid was compromised? And so this is significantly different. And again, 8 years ago, we weren't thinking in terms of microservices and the exposure that those bring. So I'll give you a quick interlude here on one way that it's possible to detect some of these kinds of attacks. Apart from our commercial product, we put out a free thing called Canary Tokens, and it sits at canarytokens.org. And this is, it's basically an updated take on an old concept where a honey token is some sort of piece of information that when you see it, you know badness has happened, because it could be, for example, a credit card number inserted into a database that credit card number isn't a real one, and if you ever see it go past in the wire, you know someone's grabbing your database. But the honey token idea has been around for a long time. Canary Tokens is our take on this, but we've now tried to jazz it up a little bit and make it really easy to use. So you basically go to the website, you choose the token type, and there's a bunch of them. So one of the ones I like particularly, there's a PDF document you can grab that'll tell you if it's opened in Adobe Reader, but even if someone cancels so in Adobe Reader you get a pop-up if something tries to contact the network. Even if they hit cancel, at that point the Canary token's already fired. There's some network stuff that happens before that pop-up occurs. So I like the PDF one. But there's other ones, the AWS key we'll talk about shortly. The idea here though is that you go to canarytokens.org, you give us an email address, that's how we're going to alert you. We give you back either a file or a little piece of information, or maybe even a piece of script. You deploy these things across your network, and if they get triggered, you get an email. So it's a very simple idea. So if we come back to this notion of where you've got these microservices, how would you know if you've been attacked, and how would you know if you've been compromised? One example I'll use here is Salesforce. Does anyone use Salesforce at their company? Is it not a thing? Some people, okay. No, so this isn't and they got hacked. It doesn't. That's not how the story ends. Yeah. No, it's not like that. In fact, this is a positive thing for Salesforce. So if you use Salesforce, if your sales team are using Salesforce, and you're the security person in that organization, one of the questions you should be asking yourself is, how do I know if any of my salespeople's Salesforce credentials are compromised? Because you don't run that system. So maybe you pull logs from Salesforce. Maybe, probably not. In general, those sorts of external dependencies don't get a lot of attention. But there is a way that we can do this, right? So we combine the idea of Canary tokens with these external services. So this is the Salesforce dashboard. And what the Salesforce dashboard lets you do is you can create items in the dashboard. So you can effectively create links or actions and links. So you'll see over there it says export all customer data with an export link next to it. So what we've done here is we create a Canary token at canarytokens.org. I'll just quick side note, we've got Docker images, you can deploy your own token service, so it doesn't have to be that domain. But you create a Canary token, which is going to give you a URL, right? It gives you a URL that looks, I know the resolution's a bit crap here, but you get a URL in the middle, and now inside of Salesforce, we take that URL and we create a link over here. We give it a nice juicy name like export all customer data. And then if anyone, so that's what the link looks like, and if anyone clicks that link, you get an email saying that link's been clicked, right? So the person who owns the account isn't going to go and click that link. They know what it's there for. If someone else breaches this account, they see a link that says export all customer data. Yeah, of course they're going to click the link. They want to get all your customer data. That's why they're there. So that'll tell you badness is happening. So Canary Token starts to give you an idea on one way that you can insert detection points into services you don't own. Right? You don't own Salesforce. You don't really have a lot of control over what happens there. But you can insert these sort of actions that will tell you when badness is on the go. So if we move on to exploitation, it's not always where we expect, right? Because the devices are getting harder, they're getting tougher to breach, but as we say, dependencies are getting fuzzier. And the dependencies are a strange thing. I credit Harun with this one. He coined what we call the Bob Ippolito problem. Does anyone know who Bob Ippolito is? Does anyone know simple JSON in Python? So if you use simple JSON, or if you use Python, it's almost entirely sure that you use the simple JSON package at some point. And the simple JSON package is written by a guy called Bob Ippolito. If Bob Ippolito ever gets hacked, like the Python ecosystem is screwed. I mean, if his package is backdoored, that thing will filter into an unknown number of Python applications. And pip absolutely allows you, pip is the Python package ecosystem. Pip doesn't require you to have two-factor or multi-factor authentication. So if Bob Ippolito is running around with just the username and password and he ever has his credentials taken, like the Python ecosystem's in a pretty bad place. And we've already seen good examples of this, right? So in the Node world, the left pad debacle took out a whole bunch of packages a little while back. So we sort of starting to get an idea on these sort of dependencies, and one of the things that we wanted to explore is how does exploitation work in a world where we have lots of these dependencies, but it's not a question so much of devices getting hacked through memory corruption or bugs in the actual devices themselves, right? So like if you ship a Chromebook, the Chromebook's a pretty decent piece of equipment, and if it's booting out of through the secure boot, through the standard secure boot, you're in a good place. But that's only if you're attacking sort of memory corruption style vulnerabilities at a low level. What about what about attacking end users? And so in this particular case, we thought we'd take a look at Atom. Who is an Atom user? We use Atom. I use Atom. So there's a few people who use Atom. So Atom, the GitHub editor, literally a hackable text editor, is what they call it. And so this particular piece of work, and you'll see from time to time, one of our guys pitches up in the corner, and that's the person who actually did the work for this section. So our thinking with Atom was, we're developers, we use Atom. We also use lots of plugins in Atom. And our sort of thinking here was, and so this is, in Atom you can install packages, plugins, extensions, and so we wanted to start playing a little bit with the idea of malicious extensions or malicious plugins in Atom. And so what Nick did is he built, so this is just a list of standard plugins, or other plugins. He built a plugin called the Touch Type Teacher. And so the idea behind what the plugin actually does is irrelevant here. But the idea is we want to know if we can get someone to install a plugin, what can the plugin do? And in this case, it turns out that, okay, so what we show here is just that it's now installed and running. And plugins in Atom are completely unsandboxed. So once a plugin runs, like that code is as if it was running on your machine, right? So it can run, and what this particular plugin is doing at this point is it's just reading every character that gets typed in the editor, and it's shipping it off to an external server, right? So it's a keyboard sniffer that's telling us what the person's actually typing. So this is an easy way to steal code. But of course, it's not just about if we can grab stuff from their editor. It turns out that when I say no sandbox, I mean completely no sandbox. So what you're seeing here is we're running, and I know you can't see it, but I'll tell you, we're running a command. So we're executing who am I, we're executing ls, and all of those things are also getting shipped out to a remote server. So the developer went onto the Atom store, selected a plugin, installed the plugin. That plugin, at that point, was a malicious piece of software that can read all files on their machine that the user has access to, can read the code. If there are keys in the repos, obviously that stuff's gone. And so what we're showing here is that we grab these dependencies, we grab these Atom plugins, and we just install them. And totally, that's what I did. Like, I wanted the Minimap plugin, and that's important. Well, I'll tell you why it's important shortly. But there's a particular plugin which shows you, gives you a map of your code. Like, it's a nice visual thing. But you just install it. I didn't review the code. And no one's reviewing the code for Atom plugins. And when that plugin runs inside the editor, there's no sandbox. So that code has full access. And so why this starts to become interesting is that, for example, you'll see tutorials on how to sideload Atom onto a Chromebook. So now, in that instance, you're no longer trying to attack the Chromebook through breaks in the secure boot process. No, forget that. You get the person to install a malicious Atom plugin, and now you get access to the stuff you actually want, which is their code and their keys and whatever else. It's a different route to that. And so the reason that I say it's like this thing, why this was interesting is that literally, and it felt like we got scooped a little bit on this, because in the same week that we spoke at Black Hat, there was a little bit of a blow up with a plugin called Minimap, so I mentioned it, and a company called Kite. So in the US, or not in the US, there's an American company called Kite, which bought a very popular plugin, Atom plugin, from the sort of sole developer who had been building it prior to that point. And after they had bought it, they then started pushing out changes to the plugin, which would show, I think, advertising. And that sort of, there was a bit of an uproar in the community. But like, yeah, totally. People can take plugins that are already there and push them out. The plugins you can set to auto, well, they can be auto-updated. And so you just have new code arriving on your developers' machines. And if you're the security team, like, good luck. How are you going to control that? You're going to start locking down the plugins your developers load in their text editors? Like, how? That's not even, I'm not aware of ways to do that. And certainly you're going to create lots of hate from your developers if you start doing things like that. So yeah, this Atom attack is, I think, quite a tricky one for security teams, and we don't have solutions. But the point here, if we take it back to the thrust of the talk, is that we deal with these dependencies in cloud environments, and this is the kind of dependency that is cropping up. And it doesn't have, I don't think it doesn't have an easy solution as yet. I mean, the one thing that I should point out is that the plugins that get deployed, and usually they get deployed out of a GitHub, you can go review the code for sure. But it's also possible to build a malicious plugin that doesn't look malicious. All it does is it pulls code at runtime from somewhere, right? And evaluates it, and that's possible. We did that as well. So you can pull code, eval it at runtime, and get the malicious code. So it doesn't persist in a repo, but it gets downloaded when the plugin is first run. Okay. So we now look at some of the post-exploitation differences. And it used to be that when you owned someone, you went for the email. Like, that's how it just always happened to go. And it's still these days possible, except email now generally is web-based. Almost everyone has it web-based. So what you can do here is, if you're trying to detect when someone is reading your email, sort of again, and we point out tokens because, as I said, it's free and we think more people should be using it. You can create, again, a basic web token, which is a URL, send yourself an email, which includes that thing, make it a link, but with a text around it that makes it juicy, so grab the latest source code or whatever the case is. And again, if anyone ever clicks that, you now know someone is reading your email. But that's old. Like that's, we've had web bugs and we spoke about this usage for Canary Tokens 2 years ago when we released them. There's a slightly different, better example. And so if you are on Twitter and you don't follow Bad Things Daily, it's a reasonable account to follow. Actually, there's some useful stuff, especially if you're on a security team. Basically what the guy's Ryan McGeehan, basically what he does every day is he posts a new idea for a tabletop scenario, but around a security incident or event or thing. And one of the ones that he posts about is, he says your company uses a popular group chat tool, say Slack or HipChat, one of those. One of your employees' credentials leak, and there's a rogue login. Person starts grabbing messages. Like, how would you know that that's the case? How would you know if someone's Slack credentials were breached and someone is going back through your Slack history? Again, you don't really have the tools to do that. Right, and so this is just a Twitter thread with someone saying like, yeah, we don't have tools to detect when people are going back through Slack logs. So how would you know? And at this point, it should be fairly obvious what I'm going to say. Canary tokens helps in this instance. So what you can do here, the basic idea here is you can stick a link in your Slack logs and again make it juicy. So if someone ever clicks the link, you know that someone's been browsing. Now there's a few, there's only one slight wrinkle here. If you just paste the link and hit enter, then everyone in the channel is going to be clicking on it. You kind of go, well, that didn't help. You'd have to ignore alerts for a few days. But what Slack does let you do is you can go back into, so this is, you'll get a bunch of alerts, and you'll get info on the Canary token. What you can do though is you can assume that someone, if they compromise your Slack, is going to search for something in particular. So if they compromise your Slack, they're going to search for passwords or kofefe, like that maybe, or secret thing. And if that's the case, you go back up into your history, find a link from 3 months ago, 4 months ago, change that link. No one's going to see it now, but if someone ever searches, they're going to jump to there and click that link, and you'll know that someone is busy browsing around your Slack. Okay. And then the last difference we'll talk about is persistence. And this is kind of, it's a little bit of a cheat, because actually I'm going to haul out a vuln that we found back in 2009, but it wasn't important back then, and now it's more important. It doesn't exist anymore, but it sort of demonstrates the idea. So when it comes to persistence, you know, pre-cloud we would be talking about persistence in terms of how can you stay on a particular machine. NSA took it to persisting on hard drive firmware so they would survive operating system reinstalls. But like that's going super low down. We say, no, forget that. You can also go super high up and target apps specifically. And one of the ways, and this is where I go back in time, is self-XSS becomes a thing. So self-XSS here just being the idea that you find a cross-site scripting vulnerability, but in a place that the user, only the user themselves can access, right? So it may be in their profile page or something that only they see, no one else sees. And like when you find them, they're sad because it's a vuln, but like no one else is going to get attacked by that vuln. And so in 2009, so we found a self-XSS in MobileMe. MobileMe was Apple's iCloud service before it got renamed iCloud. So it used to be that if you called your iPhone, if you gave your iPhone, okay, you can't see that, but that's a script, alert one script. That was the name of your iPhone. When it linked to MobileMe, there was no filtering of that data, and you got XSS into your own iCloud or MobileMe account. So that's the MobileMe account and the XSS vector. And that's just doing some fiddling to show your location is somewhere in the universe rather than specifically. But the reason that I'm going through an 8-year-old bug is these sorts of things, like the self-XSS becomes a way to persist in an application. So if you breach someone's account and there is self-XSS in that application, you can create effective, or you can create you would be able to deploy some JavaScript that gives you long-term access to the account, even if they change their password. So it's just this is a case of persistence within the application starts to become more important. But so far what we've talked about specifically has been cloud, or has been cloud in general, and I want to get a little bit more specific and start talking about AWS. And AWS is the gorilla, obviously. I mean, there's some other players, but AWS is mostly owning this market. And it's not seen a huge amount of attention from security researchers. Like there's some people playing in this area, but not a whole lot. And we use it a lot, right? And so this is sort of the usage that we, for the most part, 8 years ago, this is how we used to think of AWS. So this is us currently, but we just used to think of it as a bunch of hosted virtual machines. And that was back in 2009. We just thought of it as computers in the cloud. That's very different though. So this is, and so Theo was talking about complexity of architectures. This is Amazon's current recommended deployment for WordPress at AWS, right? Like, of which, I'm trying to find you. Yeah, so there's the actual instance. And this is all other stuff that sits around it. And so you've got a few instances to load balance, there's a memcached, there's a backend database, there's VPC stuff, there's a load balancer, there's a gateway, you've got CloudFront, there's Route 53 for your DNS. Like, there's a whole bunch of services that touch or get touched at AWS in their sort of reference architecture just for deploying WordPress. Now, it used to be WordPress was like apt-get install WordPress on whatever server you had and connected to the internet.
And MySQL.
Yeah. But now it's all of this stuff. Okay, so 2009, hosted virtual machines. 2017, like that. And you know, like we barely got a handle on how to secure Active Directory. And now we sort of on this cloud ride, and that ride started, and we're still back there trying to figure out Active Directory. And at the end I'll mention why Active Directory specifically. So if we start to talk about, or just visually try and gauge complexity. On the left-hand side, that's AWS's public API. There's about 3,100 public APIs that you can call at AWS. On the right-hand side is the GNU libc library. It's got 800 functions that it exposes. So like in terms of complexity, one's a hell of a lot more complex than the other. And this kind of makes sense because the one is just a single machine. This is a lot more than that. And when I start to talk about, there's not a lot of researchers who look at AWS, there's a whole lot of people who look at GNU security, not just GNU obviously, but there's a whole lot of people who look at host-based things, but not so many people looking on the left-hand side. To give you another measure of the complexity, so Windows and Unix, Linux, like if you talk about file permissions, there's a handful of them. If you talk about process permissions, you're talking in the order of tens if you get into like capabilities. Amazon's got about 2,400 individual permissions you can set. And so you're talking about tens versus almost 2,500. These are very different beasts. So you might even call them fantastical beasts. It's clearly more than an operating system or just a computer, and so it needs a fresh look. So I'm now in my other personality, and you'll see that we're now in, effectively it looks similar, but this is now specifically AWS focused. And so I'm going to look now at a few more steps than we've covered previously, and specifically going to look at, we're going to start with Recon. And Recon here in an AWS sense. And so if we start to think about it at the very basic level, identifying someone or an account inside of AWS happens with their 12-digit account ID. So 12 digits, there's 1 trillion of them. And we want to try and figure out if there's a way for us to discover new account IDs. The reasons for that will become apparent later, but we want to know if we can start to discover account IDs. Now the one option is a simple brute force enumeration, right? So we can simply wait for, or we can find, if we can find a way to distinguish between a valid and an invalid one, we can just try and enumerate all trillion account IDs. And what we need here is a discriminator, something that tells us if an account is valid or invalid. And if you go through the AWS API, you'll find there's a whole bunch of them, actually. This just happens to be one, excuse me. But there are other ones. And so if you make this AWS call, then what you'll find is that for an invalid account, you'll get a response that looks like that. For a valid account, you'll get a response that looks like that. And that works, but it's super slow. Right, so there's a trillion of them. We went looking to see if we could get numbers on account or AWS signups. I mean, there's not public information. It looks like there's somewhere north of 1 million users.
When was that call made?
Which?
The screenshot that you just showed.
That one?
Yes.
When was it made?
Was it against an account that you own?
Yes. Oh, no. So this would have been an account we own, yeah. So
can you do that with an account that you don't own?
You can do this with any account, yeah. So here what you're doing, if we go back, so you put in, so anyone can make this call if you've got an API key, and then you just put in that place, you put in an account ID you want to check. So you can run this with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 1, 2, run it. If this is a valid account that I don't own, I'll see that.
And which AWS key did you use to auth that call?
So that key is one tied to one of our accounts.
Okay, so you made a call impersonating your account that you own against another account.
So it happens that in this case, this isn't an impersonation call.
No, you acted as John, and John owns John's account, and you made a call as John,
yeah.
But you told AWS to create an IAM policy role. What is that, a role?
Yeah, right.
Pete's account.
Yeah, so we're not actually, we're creating a role in our own account, but this one, what we're doing here is there's a principal. Yeah, so
Gotcha.
we're giving a permission, and the principal we say is this account.
Gotcha.
When you write the account, Amazon tries to validate that principal exists. Okay. So, but this is just one, there are others. And so what we've got is a call that'll tell us if the account ID is valid or not. And so as I said, it's super slow. So we started with one of our valid accounts, and we just started incrementing the counter, and the next account we found was about 32,000 accounts or numbers away from ours, right? So it's a very sparse space. So you can enumerate, it's going to take a long time. So then the question becomes, well, if we can't really enumerate them, just because we don't want to sit that long, and note, I don't say it's impossible. Like, I think it would be an interesting thing to at least try. But we didn't have that sort of time. We said, well, let's possibly try and find them. And it's the internet, so of course you're going to find stuff. People put out their account IDs. This is the Amazon forum, so if you go look on the AWS forums, people paste their account IDs there happily as part of resource identifiers. Amazon specifically say in the forums, don't post your account ID, but like that happens. You'll find them on GitHub repos, you'll find them on Stack Overflow posts, Pastebin. Funnily enough, you'll also see them in talks on AWS security, where it's the people doing the talk use their own accounts as examples, and account numbers up there. But like with all of Amazon's advice, the honest truth is they also don't treat them with a whole lot of privacy. So this is the list of AMIs. This is the public list of AMIs, and Amazon lists all the owners there. So you can get, you can find the account ID for like fairly official-ish accounts, like the people who publish in the official Debian images or the Amazon images, that sort of thing. So you'll get those account IDs. And we'll come back to why this starts to become important. But if we're speaking about AMIs here, and this is an attempt at a segue, we're speaking about AMIs, they're often stored in S3 buckets. Let's look at S3 buckets. How did that go? All right? No. The S3, so if we've tried to enumerate account IDs now through discovering them on the Amazon interface or through enumeration, there's other ways that we can try and find out Amazon account IDs. And so one of them is through S3 logs. S3 is, and I know that, like if you're not familiar with AWS, a lot of these things is just word soup rushing over your head. So if anything isn't making sense, like I can totally do a sidebar on any one of them. But S3 is Amazon storage service. So you can create a place, you can create what's called a bucket, and you can upload stuff into a bucket and upload objects into a bucket, files into the bucket. You can download them out of the bucket. And each of those buckets has its own configuration. And one of the things you can do is you can enable logging on an S3 bucket. So whenever the bucket is accessed, a log is created. And you can also limit that bucket to only allow logged on, authenticated Amazon users to browse the bucket, right? And so where this is going should be pretty clear. What you can do is you create a bucket, enable login, limit it to authenticated users, and then you send an email to someone saying, check this bucket, or you get them to click the link. You know, it's always that other problem, get them to click the link. If they click the link and they browse the bucket and they're logged on to Amazon, you get their account ID. Now, if you create unique links, then obviously you can correlate that with the account IDs, right? So the idea here is you create a whole bunch of unique links on your bucket, you spam that at a whole bunch of people, and you see if anyone clicks through and you'll see the link coming through, you can correlate that with their account ID and their email address. So this gives you a way to tie an account ID to a specific user, specific email address. So this is another way that you can get account IDs. There's been a whole bunch of work previously on trawling these S3 buckets. So as I said, an S3 bucket is a place, you can think of it as a URL that you upload files to, and then you can download them at a later point. And those files have, or those URLs, have predictable components that you can start to guess. And so there's this whole part of S3 security, which is people trying to find S3 buckets that have no permissions on them. And if you can guess names, you can guess S3 buckets. So I'm not going to talk too much about S3 bucket discovery. There have been, there's stupidity that happens all the time. It's one of the places that you'll often see with AWS security news stories anyway. But it'll be something like someone stored classified data in an S3 bucket and forgot to enable the permissions on it. So now anyone can browse the bucket and download classified data. It's that sort of thing. And as I said, this is a well-trod path in Amazon security, in the Amazon security space. So much so that I think just recently they released Macie. I think the tool is called. It is Macie, right? M-A-C-I-E. It's like in the last week, or I think even in the last week, where they, through machine learning, whatever, magic or sleight of hand, they attempt to try and figure out if you're exposing stuff that you shouldn't be exposing in an S3 bucket, and then they send you a message. So Amazon recognizes S3 buckets, open S3 buckets, as a problem, and they're, credit to them, they're deploying, they're trying to help their customers. But the idea here, the reason I'm bringing this one up, is that the basic approach with S3 buckets is you just sort of guess names for buckets and you try and browse them and see if there's anything there. It's another enumeration attack. This is the kind of thing that cloud makes possible. There's a single point where you need to start to guess names, right? So on S3, you start to guess names. It's not like everyone has their own infrastructure spread around. There's one place, S3, and at S3 you start to guess names. And names have to be globally unique. So if Voss creates a bucket called Voss, no one else can create that bucket called Voss. So, but it's unlike, like, if Voss wants to create buckets, they might have buckets like Voss Dev, Voss Production, Voss Documents, and you sort of start to generate lists like that, and you're trying to look for them. So that sort of enumeration search has been done a lot. But those sort of enumerations aren't only effective against S3. So there is another service at Amazon called the queuing service, SQS. And SQS, so it gives you a programmatic queue, the queue being you put stuff on at one end, and then you've got workers at the other end that read stuff off the queue and they process the task and they put stuff on another queue, and there's queues upon queues upon queues. But Amazon have a built-in queue service, so you don't have to try to deploy your own, right? You just set up a queue through a web interface and it gives you a URL, right? You get a normal, regular URL. And if you can, with that URL, you can start to interact with the queue. Those URLs are made up of, they have a regular form and they have two parts to them. The one is account IDs. We've got account IDs. Cool. The other one is there's a name of the queue. Well, we saw with S3 buckets you can start to guess those parts, right? So we don't want to guess the account IDs because there's a trillion of those. It's going to take us a while. But we've got some account IDs and we can start to brute force queue names. And in truth, just like you had people posting their account IDs onto the forums and Stack Overflow, they also paste their queue URLs all over the place. So this is one of the ones that we found. We went looking for more. These are more queues. And why this stuff is interesting is that an Amazon queue is, it's by default not open to the world, but it can be open to the world. It's like, it's either not or is. There's no gray point there. Like it's either open to everyone or it's limited to the owner of the account. And so we went brute forcing stuff. We found a whole bunch of queues, but didn't find a whole bunch of open queues. We found some open queues. This one being one of the ones. So here we're querying someone else's queue, and you can see, like it's a test queue, but when they set it up, hadn't closed it down.
But even with a test queue, you've got their schema, you've got their content, you can infer, like a test queue, or like test data resembles pro data.
Yeah.
Actually, there's a bigger problem. SQS versus S3. SQS will be your raw data even before something like Celery consumes it. So everything that you might actually glean out of it, like customer data, will still be in the queue.
Right, yeah, if it hasn't been processed yet, obviously. The one thing with the queue is that it's usually short-lived.
Yeah.
But look, we didn't find a whole bunch of these queues. I just want to put that proviso out there. But they are there. Like, if you go looking for them, we'll find. So that takes us to, so that's sort of the Recon side finished. If we start thinking about compromise as it applies to AWS, this one also has had lots of attention in recent times. So I'm going to go through some of the well-known approaches quickly, just so we can sort of get them out the way, and so we cover the previous work in this place. AWS credentials, for the root credentials, it consists of an email and password, and maybe a second factor. And this is originally how you used to sign on to AWS. Those can be lost in the same way that all credentials can be lost, phishing, blah, blah, blah. Okay. The next sort of way that you can authenticate to AWS is through API keys. And this has also received a whole bunch of attention. So you can create API keys and get programmatic access to Amazon's API. And again, these keys also have had a whole bunch of work tied to them, where you can, people will commit these into repos, or they appear on Pastebin, or whatever the case is. And when they get found, then they get used, right? So someone sees that you've committed AWS API keys into your GitHub repo, they get pulled out, and then someone's running cryptocurrency mining stuff on your dime. And that's happened a bunch. So much.
You wonder why you get a bill of tens of thousands of dollars.
Yeah. Have you been there?
I've heard about it.
Yeah. Yeah. So it totally happens. And so much so that Amazon at this point, GitHub scan code, as far as I understand, for API keys, Amazon scan code.
We scan everything.
Yeah. It's like, in fact, it's a bit of a pain.
Stack Overflow throttles us.
For the scanning.
We end up in their blacklist the whole time, and then you can't Stack Overflow.
Yeah, I can imagine. Like, but it's the kind of thing that they should be thinking about. Like, it generally is.
Yeah,
it's the thing that's biting.
To be honest, you shouldn't even be using the keys directly.
Well, that's the whole story.
There's enough key management, IAM roles. There's 100 things you can do.
No.
It, like, should and yeah. What happens? These are different things. So we talked about credentials, we talked about keys. So the new hotness from an Amazon perspective are temporary keys, where the idea here is that even if you lose a key, the key is only valid for 15 minutes or half an hour. So even if it gets lost, even if it gets committed to a repo, the window in which it can be used for badness is a short window. The one thing to point out is that there's nothing that magically ties a temporary key to the instance that's using it. Like, it can still be stolen and be used elsewhere. It just has a limited lifetime. That's it. And the way that Amazon work, so I'm not going to dive into it, but you assign a role to a resource like an instance or a Lambda, and it can go and fetch temporary keys when it needs them. And so the main difference here is that they're just temporary and they have short lifetimes. So it makes it really hard to try and commit them to a repo, because your code is going to break in 15 minutes time. So you won't build it that way. And then there's one other aspect that I'll talk about. And it's more of a side note. And it's just because we haven't seen this reference a whole bunch. But there's a fourth way that you can authenticate to the Amazon API. It's through a thing called an identity document. And we've seen them primarily with CloudFormation. It's one of the Amazon services. So we don't know where else they were used. And again, the one thing to point out here is that identity documents also are not magically tied to the instance on which they're found. If they can be exported, they can be used elsewhere. But that's all I'll say about that. Okay. So if we return to this idea of compromise on AWS, what does that look like? And one of the ones that I want to talk about is inter-account sharing. So there are a whole bunch of resources on Amazon. Some of those resources can be shared between accounts. So with my account, I create an AMI, a virtual machine. Others got his account, and I can, in the Amazon interface, I can share my AMI with Azza. And basically what I need to do, or what I need for that is his account ID, right? So if I know his account ID, I can share an AMI with him. And that sharing has got an interesting property because, well, it's got two. The one is that he's got no say in the matter. He can't say, don't share it with me. It will be shared. And he's not notified when it's shared with him. So if I share an AMI with him, he doesn't know this. All he sees from his perspective is that when he looks at his list of private AMIs, there's another one there. But he doesn't know where it's come from, or he sees an account ID, but he doesn't know whose account that belongs to. And this starts to become, I think, kind of interesting. So you can, for example, create an AMI with a name like EC2 Linux Preview 2017 Q4, and share it with a bunch of account IDs that you've discovered elsewhere. And then in that private list, they'll see that AMI pops up. And so you can sort of broadly try and target a bunch of accounts, or if you know specifically how another account, what they do and what their business is through perhaps the targeted account ID extraction where we use the S3 logs to tie an email address to an account ID. If we can get someone's specific account ID, then we can share an AMI with them specifically tied to something that they do, possibly how they name their things. And so at this point, what you're hoping for is that someone clicks on this particular virtual machine, launches it, because if Azza launches the virtual machine I shared with him, now I'm running code in his account at his expense. And if he assigns a role to this, it also means potentially I get permissions in his account. And so that idea of permissions, and we're sort of diving a little bit now into specifics well, diving deeper into specifics on AWS. When you run in an instance that has got permissions to run, like a role, or even if it's got API keys, or even if you find API keys. So actually, let's use that example. That's going to be an easy one. If you discover API keys on GitHub, you just get there's a key and a secret. If you want to figure out what that key pair can do, or that credential pair can do, the one way is you can issue a specific call to say, show me the policy for this key. So there's an IAM get policy call. But it's also possible, it's often the case that that call is denied because you don't actually want to give that to the key. So by default you deny and you only allow the stuff you actually want the key to do. So you find this key, you say, cool, I found a key, I'm going to ask Amazon for the policy tied to the key. Amazon comes back and says to you, sorry, I'm not going to give you the policy. At that point you might go, well, no, I don't know what the key can do. But why give up at that point, right? Because we know all of the calls that are possible within the AWS API. So one of our options is we can take those 3,000 calls and this is in broad terms, this is what we say. You can take those 3,000 calls. Some of those calls have side effects, so the side effect may be that it's going to launch an instance or delete something. Okay, so let's not do that, just in case we do have permission and we start breaking stuff. But we can look at the prefix of all of those calls and pull out the get, the list, the describe, and that's about, I think it's about 900 calls. And then we can call every one of those with the key that we found and see, can we make the call, or can we not? Do we get an authorization error, or do we succeed? And in doing so, we can brute force the permissions tied to this policy without us actually having to download the policy. So it's a long cut, if you like, for getting the policy rather than the direct method. There's some interesting aspects here, because in building this, you get a very clear sense that the AWS API was not written by one cohesive team, but by a whole bunch of separate teams. And so I think there were somewhere in the order of like 14 separate authorization exceptions. But like, they're different exceptions. It's not the same exception. They're different. They're all authorization denied of various guises. So this is the script running with a particular key pair. This is the script running with a particular key pair. It's just a Python script, and as I said, it's going to brute force. It's going to brute force a whole bunch of the calls.
Are you running this against with the different accounts keeping?
This is a key pair that we found.
Okay.
Like broad terms, it's the key pair that we found. Okay. So we start with EC2, we start with S3, you start with the ones that are most likely, and then you sort of go down to the low ones. But in doing that, we can discover what the capabilities are for this particular key pair, or if you're in an instance for the role or whatever. But the idea is that you don't need to rely on IAM get policy to figure out what the permissions are for a given key pair. So if we sort of cross out our compromise there and we move on to lateral movement, usually it used to be the case, compromise got you into the network, onto the beachhead. At that point, you're now trying to move through the network, and that's the idea with lateral movement. So within AWS, what does lateral movement look like? Well, if we gain access to an AWS account, possibly we want to run code on individual AMIs, right? Because there's stuff happening on the AMI that we might want access to. So if we have access to the account, how do we get access to the running, the running instances, not the AMIs, the actual running instances? And I'll give a shout out here. There's a guy called Daniel Grislick. He works at Atlassian, and he's done he's done a whole bunch of work on AWS. And in fact, he's a little bit shouting into the wind on the top of a cliff, because he's been talking about this for a bit and hasn't got a whole pile of traction. And so what he found is that, and this is an expected behavior in EC2, but if you take the user data field, user data is how you parameterize virtual machines inside of EC2. So every virtual machine that runs, you can give it a little bit of unique user data, and that user data will set up that virtual machine as a unique virtual machine. And so what you can do is you can simply just put in shell script there, and when the virtual machine starts, it runs the shell script that's in there, right? So what this now looks like, if you're trying to move to a different, or if you're trying to execute code inside of a virtual machine, you can paste some shell script here, stop the instance, start the instance, and whatever code you have would now run. But it does require you to stop and then start, and that's a noisy operation, which certainly if they're relying on a particular service inside that instance, it's going to cause issues. So we wanted to see if there were other options, and there are a few. There's who uses CloudFormation? Okay, there's a few people. So like in broad terms, and again, Amazon has got so many services, and if you're not super familiar with them, it is just this soup of words. But CloudFormation is it's a service that you set up a template file, which is, in this case, it's in JSON. But the template file describes how many virtual machines, what the networks look like. It's an orchestration, kind of an orchestration solution for Amazon. So you can, that reference implementation of WordPress that I showed you with all the bits and pieces, all of that can be packaged inside one single CloudFormation template file. And what you get is something that looks like this, where you get a bunch of these things. So these are EC2 instances, but this could say the template is WordPress, and you hit launch stack button over there, and Amazon parses out this whole JSON file, reads out all the things that needs to happen. It does all of that, and then it